We've in the past, maybe in your junior class, you've tried to understand a few things related to heat, calorimetry, and so on and so forth. What I'm going to quickly do is a recap of things that you already know. Now, first of all, when we talk of calorimetry, we are talking of flow of heat from a hotter body to a cooler body. We are not talking of the mechanism of flow. The mechanism of flow of heat from a hot body A, if there is a hot body A, and there is a cold body B, that means if the temperature of A, TA, is higher than the temperature of B, which is TB, if TA is more than TB, and by some means they thermally interact. I mean, there could be heat transfer between the two by various means, and we are not as of now interested in how exactly the transfer of heat between A and B takes place. It could be conduction, convection, radiation. That will fall within the jurisdiction of another unit called heat transfer. But right now, let's say if there is flow of heat from A to B, eventually what happens is both A and B arrive at a final common temperature T. The hotter body cools and the cooler body heats up. The temperature of this will decrease and the temperature of this will increase, and that will happen. There will be exchange of heat between A and B till such time that their temperatures get equalized. We then say there is a state of thermal equilibrium. Now, an important aspect of the heat lost or gained by a body when its temperature rises or its temperature decreases is given by the following result. If there is a body of mass m, and it's at a temperature T1, right? And suppose its temperature rises to T2. Say T2 more than T1. That means it must have gained heat. Its temperature rises means heat gained. It must have gained a certain amount of heat, and the amount of heat gained by this body, commonly designated by Q in calories. Calories is the CGS unit of heat, is given by mass into a property of the substance which is called the specific heat, S, into change in temperature delta theta. In this case, delta theta is the increase in temperature, which is final temperature minus initial temperature, change in temperature, mass specific heat into change of temperature. So what we really have is a prop mass, which is of course, the amount of substance that you are dealing with, S, which is called the specific heat of the substance, which is a property of the substance. It has nothing to do with the mass or the temperatures involved. It's a property of the substance and is defined as the amount of heat. See, S, as you can see, is Q divided by M into delta theta. So S, as you have seen before, is the amount of heat required to raise the temperature of unit mass of a substance through unit degree centigrade. S is a property of the substance, which is the amount of heat that is required to raise the temperature of unit mass of a substance through unit degree, right? That's specific heat, and that's documented, and that's obtained through experiment. For water, the specific heat is found to be 1 calorie per gram per degree centigrade. For ice, the specific heat is found to be 0.5 calories per gram per degree centigrade for ice, right? And for different substances, copper will have one specific heat, aluminum will have another specific heat, and so on and so forth, right? So specific heat is the amount of heat required to raise the temperature of unit mass of a substance through unit degree centigrade. And if there is increase in temperature, if there is increase in temperature, that's heat gained. If there is decrease in temperature, then that's heat lost. Heat lost, if the temperature decreases, then this delta theta will be the decrease in temperature, and this Q would be the heat expelled or the heat lost, right? Increase of temperature would mean this Q is heat gained, right? Decrease of temperature, that means if T2 is less than T1, then delta theta is the decrease in temperature, and the heat lost or heat expelled by the substance is going to be the mass of the substance into specific heat into change of temperature. Yes or no, right? In that context, we have another entity defined. Which is called thermal capacity. Thermal capacity or heat capacity of a substance is H, which is mass into specific heat. Mass into specific heat, right? Which is like Q. It's like Q. H is the same as Q when delta theta is 1. When delta theta is 1, isn't it? If delta theta is a unit degree, it's like 1 degree, then Q becomes equal to H. That means, what is H? H is also the amount of heat required to raise the temperature of the given mass by 1 degree centigrade. That's a heat capacity of that substance. That's a heat capacity or thermal capacity of the substance. This is what? M into S, mass into specific heat, which is the amount of heat required to raise the temperature of the given mass of the given substance by 1 degree centigrade. That's the thermal capacity or heat capacity of the substance or the matter contained now. So heat that goes to change the temperature, is sensible heat, right? Now, suppose I have a solid substance, right? And that's at temperature T1. And its specific heat is S. And its mass is M, say, right? Now, when I keep supplying heat to it, the temperature initially rises. So first thing that happens is temperature rises, right? Temperature becomes more than T1, right? But will the temperature keep rising forever? No. After a while, it gets into a state, as you keep supplying more and more heat, it gets into a state where temperature remains constant for a while. Right? Now, why does it remain constant after a while, even though you're supplying more and more heat? What really happens is, this is the time when this solid starts to change its phase or change of state. Change of state takes place. When the temperature remains constant, there is change of state. All the heat that you're supplying during this process is not enabling increase of temperature. The solid is getting converted into liquid. And this happens at what temperature? It happens at what is called the melting point. At the melting point, there is change of state. Solid to liquid takes place. Now, when there is conversion from solid to liquid, and if I have m grams of the solid at its melting point, to be converted into m grams of liquid at the melting point, then the heat required at the melting point, Tm is the melting point, is going to be given by mass into a property of the substance, which is called latent heat of fusion. This is called latent heat of fusion. The heat required to convert at the melting point 1 gram of the substance solid into 1 gram of the liquid is called the latent heat of fusion, right? So if I have m grams of the substance, the amount of heat required at the melting point to convert it into the corresponding liquid at the melting point is mass into L, where L is a latent heat of fusion. Its unit is obviously calories per gram. L is measured in calories per gram. So we have solid to liquid. This is what is happening, right? Solid to liquid, there is latent heat of fusion. There is latent heat of fusion, isn't it? There is latent heat of fusion involved. In fact, so when you're converting from solid to liquid, you require a certain amount of heat, which is called latent heat of fusion, and that's obtained by m into L. L is a property of the substance called the latent heat of fusion. And for water, ice to water, when ice at 0 degree centigrade is the melting point of ice, to water at 0 degree centigrade, what you would require is latent heat. And the latent heat of ice, is roughly 80 calories per gram. That means every gram of ice at 0 degree centigrade will require 80 calories of heat to get converted into water at 0 degree centigrade. And this is not sensible heating. This is latent heating. Heat that does not manifest itself in terms of change of temperature, right? So for ice, the value of latent heat of fusion is 80 calories per gram. Now if I had, that means every gram of ice at 0 degree centigrade, 0 degree centigrade is the melting point of ice, will require 80 calories of heat to get converted into water at 0 degree centigrade, right? But if I have water to convert into ice, if I had water to convert into ice, then that is not fusion. That is solidification. See, from here to here is fusion, from ice to water is fusion, but this is solidification. And when solidification takes place, that means when water converts into ice, then we have what is called latent heat of solidification. Heat will be expelled from the system. From water to ice, heat will be expelled, and the process is called solidification. And the value of heat that is expelled is mass into latent heat of solidification. But the latent heat of solidification is the same as latent heat of fusion. That means the amount of heat required to convert 1 gram of ice at 0 degree centigrade to 1 gram of water at 0 degree centigrade would be the same as the amount of heat which is expelled to convert 1 gram of water at 0 degree centigrade to 1 gram of ice at 0 degree centigrade. So we have two kinds of latent heat between ice and water. From ice to water there is fusion, and from water to ice there is solidification. Both involve the same property L, having the same value. One, of course, from ice to water we call it fusion. From water to ice it's called solidification, latent heat of solidification. So L is a property whether from water to ice or from ice to water. That means from solid to liquid or liquid to water, it will have the same value, right? All of these things, you know, I'm sure it's just a quick recap of things that you've learned in the past. Now, so you have now liquid at your disposal. After you have supplied it enough heat to change state from solid to liquid, now you have liquid at the melting point. Now if you supply more heat, the temperature of this liquid will rise. It'll keep rising, but after a while, at a certain point called the boiling point, at a temperature equal to the boiling point, if you supply more heat to it, then for some time, there is going to be no manifestation of heat in terms of change of temperature. Temperature remains boiling point. That is when a change of state is taking place. Change of state. This time a change of state from liquid to gas. This change of state is liquid to gas or vapor. And if I have m grams of the liquid to be converted into m grams of vapor at the boiling point, m grams of liquid to m grams of vapor at its boiling point, then the heat required to do so would be Q equal to mass into L. This time this L is latent heat of vaporization. Its value will depend on the substance. For water, its value is 540 calories per gram. For water, it's 540 calories per gram. Yes or no? So every gram of water, for example, every gram of water will require at its boiling point. What is its boiling point? 100 degrees centigrade. Every gram of water at 100 degrees centigrade, and of course 1 atmospheric pressure, will require 540 calories of heat to get converted into steam at 100 degrees centigrade. And so water to steam is vaporization, but steam to water is condensation. And one thing that you must bear in mind is that the amount of heat required for vaporization at the boiling point and a given atmospheric pressure, the same amount of heat will be expelled when condensation takes place. So latent heat L of vaporization is the same as latent heat of condensation. So now that makes, of course, life really simple for us. And one last bit in terms of calorimetry which you might want to know is the following, so that we can get started with some basic problem solving, is the following. This is what you must know. If there is heat transfer between two substances, there is mass m1, specific heat s1 and temperature T1. This is mass m2, specific heat s2 and temperature T2. Let's say this is hot and this is cold, right? So there would be heat exchange from a body at higher temperature to the body at lower temperature, and they acquire a common final temperature T. So this would have lost heat, this would have gained heat. Heat lost by this is going to be what? Mass specific heat into change of temperature, T1 minus T, right? Its temperature would decrease, right? So T1 minus T, and that must be equal to heat gained by this, which is mass of this into specific heat of this into gain of temperature is T minus T2. That is, heat lost is heat gain. Heat lost is heat gain. That's the principle of calorimetry. Right? Or we can even say summation heat gained, as if both bodies are gaining heat. Summation heat gained is 0. Let's say each is gaining heat. Of course, one would be positive, the other one would be negative. That means heat gained by this is m1 s1 into T minus T1, plus heat gained by this is going to be m2 s2 into T minus T2. That's equal to 0. Realize that this statement is essentially the same as this statement. When you do not know whether T1 is more or T2 is more, assume that both are gaining heat, and the algebraic sum of the heats gained by both must be 0, right? This then brings us to a very important principle of calorimetry. Heat lost is heat gain, which is just a statement of conservation of energy. We are assuming that heat doesn't go anywhere and there is complete exchange between these two, then this equation will hold good. Thank you so much. Bye-bye.